Welcome to this second lecture on lattice Boltzmann method. So this lecture is on Boltzmann equation, like how to derive it. Before doing that, we'll ask ourselves what is simulation which we are doing, which we are eventually going to do after discretizing Boltzmann equation. So the experiments performed on a computer or numerical experiments is called simulation. So this is what Nobel laureate and physicist Richard Feynman had to say about experiments. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It does not make a difference on how beautiful your guess is. It does not matter how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is. So whatever results we get after doing simulation, in case of fluid dynamics, it's velocity field and pressure field, we are going to validate this with experiments or by performing experiment. But performing experiment is time consuming and expensive. The standard experiment which is performed, which if you want to know about the aerodynamic design of a car, so either you have the full scale car or the model of the car, you place it in a wind tunnel and you have smoke around it, and you compute what is known as drag, or the drag force on the car. So instead of, like, we cannot afford to build a wind tunnel, so what we are going to do is we are going to create the same car on a computer, and we can have flow around it. The important parameter is the Reynolds number. So this is a velocity field or velocity contour at some instant of time. So we can compute drag coefficient using this as well. Then we can compare these two, how accurate our numerical method is by compared to the experiment performed in a wind tunnel, on a real car, One more way to define simulation is creating videos of this real world phenomenon using physics. So here you can see the velocity contour at some instant of time. You can have many such velocity contour. You can combine them all, and create a video. This simulation of like the flow around car will be done in the coming lectures, where you approximate the geometry of this car using staircase approach. We'll look at one more example. You can see a picture of a stream of water moving in a channel or an open channel. This is usually found in rainy seasons in India. You have many such channels. Seeing this picture does not provide any information like the velocity or the velocity field or the pressure field. That is the question which we ask by looking at such a flow: how fast it is moving. There are two ways to analyze such a flow. One is known as Eulerian way and the other is Lagrangian way. So first we'll talk about this Lagrangian way. Lagrangian way is nothing but tracking. So you are with the flow and move in the flow, which is called a control mass approach. This is done in an experiment called PIV, which is called particle image velocimetry. What you do is you seed this flow with these particles, and then you track these particles as they move with the flow, and you have the path of that particle, and using which you compute the velocity. One more way is the Eulerian way. So you stand here at some fixed position and you have a control volume. There is inflow and outflow: inflow of mass flux, outflow of mass flux, inflow of momentum flux, outflow of momentum flux, and inside the control volume there is a change in mass flux or change in momentum flux, and you can like derive this governing equations. So here, see, I've in a computer you create such a channel. So this is the wall, then there's inlet condition or the entry, and then there's exit or outlet condition. So here is the Eulian frame of reference: a person fixed, seeing this is the control volume, seeing what is coming in and what is going out, and what is the change within the control volume. So the governing equation is the conservation of mass or continuity equation and conservation of linear momentum, NAC, which is nothing but Newton's second law applied for a fluid. So this is Newton's second law. Summation of forces is mass into acceleration, mass is density into volume. Here we are dealing with the control volume. So force per control volume. So density into acceleration. Yeah. So the acceleration is nothing but rate of change of velocity. So when you sum up these forces, so what are the forces acting on like on a fluid? So you have surface force and you have body force. Body force is gravity. Another example for body force is electric force or magnetic force, which will come up in magnetohydrodynamics. We'll take such a problem, yeah, in upcoming lectures. And in surface force, you have pressure force and viscous force. So pressure is a scalar. So to make it a force, which is a vector, we perform gradient operation on a scalar field. It becomes a vector. Yeah. And viscous force is due to the stresses. The stresses could be normal stresses or tangential or shear stresses. Yeah. So stress itself is a tensor. So to make tensor into vector, you perform divergence operation. This is explaining Navier-Stokes equation in a simple way. Yeah. And this is rate of change of velocity, which is acceleration. This is Lagrangian way to write dv by dt. So in Eulerian way, you can use Taylor series and expand this. So you'll get this. One is the first term is the temporal or local, and then you have the convective term. Yeah. So you can refer to like the full-fledged derivation of Navier-Stokes equation in like any standard textbook and how they approximate the shear stress, yeah, whether the fluid is Newtonian or non-Newtonian. Yeah. So if you solve these Navier-Stokes equation, which don't have like the analytical solution using numerical methods like finite difference method or finite volume method, where they use algorithms like simple R and simple C, you can get the velocity field and the pressure field. But in Boltzmann equation, we don't directly get this velocity field and pressure field because we'll be solving the Boltzmann equation. In Boltzmann equation, you'll be dealing with F, which is called particle velocity distribution function. So the same channel in same channel will be like this. You'll have digital particles in every control volume. So each control volume is populated with 9 digital particles, one going to the left, one going to the right, one going to the top, one going to the bottom, some moving diagonally, and there's one more digital particle which is at rest. So this is called D2Q9 velocity model. Yeah. Why they call LBM as a mesoscopic method or mesoscale? So we'll talk about this. So in microscale, you deal with individual molecules, which is called molecular dynamics. In macro scale, which is the Navier-Stokes equation or the continuum, you get directly the velocity field and pressure field. In LBM, you get a physical property or the macroscopic property from the collection of particles. So from 9 particles, you get, if you sum them, you get, for example, density, you can get the velocity at that point, you can know the pressure, you can know the temperature. That's why it's called mesoscale. You deal with this collection of particles, they give you one property. Actually, it's the moment of the distribution. So we will try to do that in future lectures, like how many moments you can get. You have zeroth order moment, first order moment, second order moment. Yeah, we'll talk about that when we are like doing MRT, where we perform collision between moments. Yeah. So F is our interest. So every digital particle has an F. So if I call this as 1, so there is F1. Then if I call this as 2, there is F2. So this digital particle will take. So it is F is a function of position, velocity, and time. So this digital particle is at certain position, with certain velocity at certain time. So after that, after performing, so in LBM it's only collision and streaming. So there's pre-collision, post-collision, and streaming. So in streaming, see, they'll be moving from this position x to x plus delta x with some velocity c. It will move with c plus delta c, and time has also passed. It will be t plus delta t. So we want to know this. So whatever it was at previous plus this. This is nothing but Taylor series. Del f by del x delta x, del f by del c delta t, del f by del t into delta t plus higher order terms. Now we'll divide this with delta t. Yeah. So when you divide this, delta t will get cancelled. So delta c by delta t is change in velocity with time, which is acceleration. Delta x by delta t is c, velocity. Yeah. This left hand side will be df by dt, or the collision operator omega at delta t tending to 0. It will be df by dt. We'll call it as omega. So this is the equation: del f by del t, c del f by del x plus fx del f by del c. we'll say there is no external forces acting, so this will go to 0 on the system. So del f by del t will be c del f by del x equals omega. Now here if you see, there are some moving to the right, some moving to the left, some moving to the top, some going to the bottom. So there's x and y. So C will have two components, which is Cx and Cy. So that's why I've written it as C vector in vector notation. Cx I cap plus Cy j cap. Similarly, this del f by del x. So there is del f by del x, and then there is del f by del y even in y direction. So that's why it is gradient of f. Yeah, in 3 dimension, del f by del x, del f by del y, and del f by del z, and c will be cx, cy, and cz. So this equation del f by del t c vector dot gradient of f equals omega is called the Boltzmann equation. There are different ways to approximate this collision operator, based on which we have BGK, MRT, then there is cascade, then there is cumulant. Yeah. This is the continuous Boltzmann equation. What we want is we want this Boltzmann equation for every digital particle 1, 2, 3, 4, 5, 6, 7, 8, and 0. So we'll call it del f by del k by delta t, and in 2 dimensions cx del f by del x and cy del f by del y equals omega. Yeah. Now there are different ways to discretize this Boltzmann equation. You can use finite difference method, you can use finite volume method, which gives rise to these so-called gas scheme, yeah, or lattice gas schemes or lattice kinetic schemes. Then you can do it using even finite element method. So, but what we'll do is in the next lecture we will talk about kinetic theory of gases, and this collision operator omega as an equilibrium distribution function. We'll try to derive that as well, and we'll discretize this Boltzmann equation using finite difference method. Yeah, that's all for this lecture. Thank you.